All right, good morning. The bell ringer is match the following words and phrases with a definition. We're focusing on vocabulary here. We have cycle, efficient network, Euler path, Hamiltonian circuit, vertex and edge. Our definitions are 1, visits every vertex. 1, starts and stops at the same vertex. 2, a connection between vertices. 3, connected but contains no cycles. 4, only crosses edges once and starts and stops at the same vertex. And 5, an intersection where edges meet. 6, crosses every edge exactly once. Okay. So what do you think a cycle is? Connected but contains no cycles. I bet that's probably it. But as we can see, Euler path crosses every edge exactly once. We knew that already from the first lesson of this unit. An Euler path is crossing every edge exactly once. Vertex is an intersection where edges meet. That's absolutely correct. Edges meet into an intersection. We call that a vertex or a node, which is a good synonym. Big bold dot, sometimes labeled with a letter. An edge is a connection between vertices. Yes, an edge is a line that connects two vertices together. Some vertices have more than one edge spanning between them. An efficient network, connected but contains no cycles. That's correct. And Hamiltonian circuit visits every vertex once and starts and stops at the same vertex. Remember that the circuit portion is just the starting and stopping at the same vertex. And of course, the cycle is the only one that remains. 4, only crosses edges once and starts and stops at the same vertex. Okay, good things. Who has good things going on in their life? Send me a message through the Google Classroom and let me know what's going on good in your life. Let's see. I've had lots of good things happen to me in the recent couple weeks. Too many to talk about, so let's just move on. Hopefully I'll start adding some good things for other people here in a minute. Learning objective. The objective is I can use Kruskal's algorithm to determine the minimal spanning tree of a weighted graph, and I can make connections between previous graph models to create efficient networks. All right, let's go on. All right, new vocab. A graph whose edges are given numerical values is called a weighted graph. Keeping all the vertices connected by a path resulting in the minimum total weight is called finding a minimal spanning tree. Now, in this particular phrase, the word spanning means that each vertex remains connected to the graph, and the word tree indicates that there are no cycles. In other words, there are no duplicate or redundant pathways between vertices. So they don't have duplicate paths through other vertices or just directly back to it. So let's move on. Following procedure known as Kruskal's algorithm can be used to find a minimal spanning tree in any weighted graph. Okay, so this only applies to graphs that have weight values assigned to each edge. So assume you start with a table of weights associated with each edge, just like I discussed. And just like the real world problem in student activity sheet 7, step 1, put all of the weights in a list from smallest to largest. Step 2, find the smallest weight in a list and include the associated edge and 2 vertices, as long as it does not create a cycle. And if it creates a cycle, we won't use it. We'll just go on to the next one, and we'll eliminate it from the list so we don't try to go over it again. And then step 3, we'll remove the weight from the list, just like whether or not it is used, it gets removed from the list. And step 4, we'll repeat steps 2 and 3 until all vertices are connected. Now, once all the vertices are connected, we go no further, because then it spans and it's a tree, okay? It's efficient, and all of the vertices can be reached by every other vertex by some method of pathway. All right, so a series of bridges will be constructed to connect a group of 7 islands. Highway department wants to make sure that a vehicle can be driven from one island to all the others in this new network of bridges. The cost of building a bridge is directly proportional to the length of the bridge. The following table provides the distance in miles between each pair of islands. As you can see, we've got 1, 2, 3, 4, 5, 6, 7 islands, and each one has a mile associated with it between the different islands. Now, these grayed out portions are just, we don't want to duplicate the numbers so as to confuse the person that's using this table. All right, so we're going to use Kruskal's algorithm. How would we do that? We would actually use this and line up all these numbers in order. So the first one that is the shortest length, that's the first step in Kruskal's algorithm. If you look back, put all the weights in a list from smallest to largest, okay? So 3 would be the smallest, and then 4, and then 5, and then 6. And then there's 2 7s, and then there's 2 8s, 3 8s, I apologize, 3 9s, and so on through 13. We're going to put those in a line. I'm not going to show you in this presentation, but you can see that the answer is in here somewhere. But what we want to know is we'll start with 3, and notice that all 3 of them start with that 3, BF. And then BC, and BC here is 4, so A, B, and D are okay. Notice it says BF creates a cycle. Well, there's no way it could create a cycle. It's the first edge we actually looked at. It would create a cycle if there was a redundant pathway. If it's the first edge, it's not redundant. So we can eliminate C. Let's go on. BC is not redundant. That means we have 2 edges from B, one going to F and one going to C. And then the next one, A, CF is 5, and then we move on. But on B, it says CF equals 5, but it creates a cycle, so we don't use it. It also says that down here at D, CF equals 5, but it creates a cycle, don't use it. Now, why would we determine that that created a cycle? If you look carefully, B goes to F, and then B goes to C. If we connected C and F, we would have a triangle, and we would have redundant pathways. So B and D are both correct in that it creates a cycle and we don't use it. So we'll eliminate A. So now we've eliminated C and A. We have just B and D left. G equals 6, and that's in both of them. And it says that we will go ahead and use it. I don't see any problems here so far. And then EF equals 6. And over on D, it says EF equals 6, but it creates a cycle, don't use. Now, it's easy to see if it would create a cycle or not. F is part of the, it would be part of the move if it actually connected. So BF and EF are connected. So we do have 2 edges going into F, but we don't have any pathway between E and B, so there's no redundant pathway. So that eliminates D, leaving only B as the proper answer. All right, now we can look at this easier. Can we find a minimal spanning tree in the following graph? Yes, we can. We'll just start at the smallest, and we'll use it. And then we'll use the 2 5s. Notice we still don't have any redundant pathways. We're just going in between here. Now, there's 6 is the next pathway. We can't use this one because we are already connecting these 2 through this vertex. So we won't use that one at all. But we can use this 6 because it doesn't have any problems. We can't use this 7 because that's already connected. This 5, this vertex is connected to this vertex by going through this pathway. We've already connected it. Now, the next number up is 8. We can't use this 8 because we've already connected these 2 vertices through this pathway here between the 2 5s. And then finally, the last 8 goes here, and that would connect all vertices together by making this move all the way across. And on the next page, we're going to show different ones, and you can see graph 1 is not correct. It has 10. We only used a 4, a 5, a 6, and an 8. Now, notice that we use this 6 here, and we didn't use the other 6. This is our efficient pathway. If you look here, 4, 6, 5, 6, 4, 6, 5, 6, 8, it is an efficient pathway, but it's not the minimal spanning tree. We look here, this was a pathway we chose as the minimal spanning tree. Graph 2 is correct. All right, now, in this last one, we're going to reflect, do all graphs have spanning trees and are spanning trees unique? Initially, when I did this video, I made a mistake, and I'm going to go on to fix this, and I'm a human. We can easily eliminate D because it says all graphs have spanning trees because Harambe climbs on them. I use Harambe as an answer just to give the students a little extra added help. I like Harambe. We'll talk more about him in the launch. But let's look at the answers that do make sense. A, no. Some graphs do not have spanning trees, making them unique. Now, initially I said this is true because some graphs do not have spanning trees. And they don't have spanning trees because they're not connected. If they're not connected, though, they're not efficient networks and they're not a full graph and it wouldn't span. So that's why it wouldn't work. We're looking for graphs that have spanning trees. Graphs that do not have spanning trees just don't qualify for this particular one. Some graphs don't have spanning trees. They don't qualify for it. If you look at some of the other ones, there's qualifiers. B, all graphs have spanning trees regardless if they are connected and are not unique. This cannot be true. All graphs do have spanning trees, but it says regardless if they are connected. In order for them to have a spanning tree, they have to be connected. That eliminates B. That leaves only C, and let's explore why that is true. All graphs have spanning trees, and that's true. We can make a spanning tree out of every graph as long as they are connected. And in the last qualifier, it sets it in stone. They always use one fewer edge than the total vertices, making them not unique. So we can have several different spanning trees, and that means that they're not unique. It's not the only spanning tree in the graph. We can have several, and that's why they're not unique. So I'm going to launch you with this. I should not still be talking about Harambe. When I say should not, I don't even mean that it's morally wrong to joke about Harambe. I mean that as a running joke, he should have had about a shelf life of maybe 2 weeks. The meme should have died shortly after the animal did. But I aim to keep his memory alive, and if it's in my class alone, then so be it. If you don't know about Harambe, he's an interesting chap. You should look into him. He used to live in the jungles. They captured him. They put him in the zoo. And a kid fell into his cage, and he was just trying to protect him, but the zoologist thought otherwise and shot and killed him. So y'all have a good day and get working on this assignment. It's SAS 8. Kruskal's algorithm. It's in the Google Classroom. Have a ball, y'all. Be blessed and be a blessing.